weak acid such as acetic acid ionizes partially. A weak acid is partially ionized in the aqueous solution. Thus, considering the following equilibrium, HX plus H2O reversible H3O plus X minus. Initial concentration of HX is C and that of H3O plus and X minus is 0. And equilibrium concentration of HX is C minus C alpha and that of H3O plus and X minus equals to C alpha. Since we know that K equals to concentration of H3O plus multiplied by concentration of X minus upon concentration of HX. This implies that K equals to C alpha square upon 1 minus alpha. Since we know that larger the value of K, larger the value of X. This implies that concentration of X minus equal to concentration of H3O plus equal to C alpha. Hence, we can say that at a given temperature T, larger the value of Ka, more is H3O plus concentration and stronger is the acid. The partial ionization of weak base can be represented by the equation MOH reversible M plus OH minus. Let the partial ionization of weak base, that is MOH, be C. Let the initial concentration of MOH be C and that of M plus and OH minus be 0. Let alpha be degree of dissociation of base. Then amount of base dissociate equals to C alpha. So at equilibrium, concentration of MOH equals to C minus C alpha and that of M plus and OH minus equals to C alpha. Since we know that equilibrium constant K equals to concentration of M plus multiplied by concentration of OH minus upon concentration of MOH. Since K equals to C alpha into C alpha upon C minus alpha, which on simplifying get C alpha square upon 1 minus alpha, which is equals to Kb. No more. The equilibrium constant Kb for base ionization is called base ionization constant. Many organic compounds like amines are weak bases to very small Kb. Smaller the value of Kb, weaker is the base. Relation between Ka and Kb. Acid ionization constant, that is Ka, and base ionization constant Kb represent the strength of an acid and a base respectively. In case of conjugate acid and base, for example, NH4 plus is conjugate acid and NH3 is conjugate base. Ka and Kb can be related as Ka into Kb equals to Kw. Now we will come to the derivation. For conjugate acid, NH4 plus H2O reversible H3O plus NH3. Since Ka equals to concentration of H3O plus multiplied by concentration of NH3 upon concentration of NH4 plus, which is equals to 5.6 into 10 to the power minus 10. For conjugate base, NH3 plus H2O reversible NH4 plus OH minus. Since Kb equals to concentration of NH4 plus multiplied by concentration of OH minus upon concentration of NH3, which is equals to 1.8 into 10 to the power minus 5. The net reaction is 2H2O reversible H3O plus OH minus. Since Kw equals to concentration of H3O plus multiplied by concentration of OH minus, which is equals to 1 into 10 to the power minus 14. On multiplying Ka and Kb, we get Ka into Kb equals to concentration of H3O plus multiplied by concentration of OH minus, which is equals to Kw, which is equals to 5.6 into 10 to the power minus 10 multiplied by 1.8 into 10 to the power minus 14, which is equals to 10 to the power minus 14. This implies that Ka into Kb equals to Kw. Hence proved. Text. This derivation can further be made to generalize that the equilibrium constant for a net reaction obtained after adding two or more reactions equals the product of the equilibrium constant for individual reactions. This implies that K net equals to K1 into K2 into K3.